Okay guys, so one of the most difficult things you do when you're doing complex numbers is sketching complex loci, right? And one of the most difficult complex loci to sketch is this equation right here, right? Arg of z minus a plus bi on z minus c plus di is equal to theta, right? And after you learn how to sketch that, the teachers, or sometimes the teachers, decide in a really nasty test question to put on the idea to find the center and the radius of the circle that this major arc is on. Right? So now most students probably don't know how to do that, right? That's probably one of the most difficult questions you can ask in complex numbers. So I am going to go through a way, and I found a formula in which you can directly plug in a, b, c, d, and theta, and you'll get out your center of the circle, and then from that you can find the radius, right? So let's start this proof, right? So the first thing that we have to understand is that I'm doing this for a major arc. This won't work for a minor arc. There's a completely different proof for a minor arc, and I'm going to go through that in another video. So what I'm going to start by doing is I'm going to start by assuming that there's a point on this major arc, like here. Right? And this point I'm going to label this point C, right? And I'm going to give it the complex number coordinate Z. So here you can see that by the definition of the properties of this type of function, if I connect these two lines together, right, this angle in here must be theta, right? That's the idea. That's why it traces out the major arc, right? And now what I'm also going to do is I'm going to assume that there is a center of the circle. I'm going to assume the center is point D right here, okay? And I'm going to give this the complex number Z0. So Z0 is the complex number. So Z0 will be some x plus yi, right? And the coordinates x comma y, that will be the center of our circle. So let's do this, okay? So obviously if I join these 2 points together, right, and everyone knows by the properties of circle geometry, the angle at the edge of the circle is half the angle at the center. Or in other words, the angle at the center is 2 times the angle on the edge. So this is 2 theta. Okay. So now we can begin our proof. Okay. The first thing that I'm going to do is I'm going to ask everyone to consider the complex number AD, okay, on BD, sorry. Okay. Now AD is the complex number Z0 minus A plus BI, okay, all on, and then BD is the complex number Z0 minus C plus DI. Right? So keep in mind, remember, you can find AD by doing the simple thing like vector subtraction and addition, right? So it works the exact same way. Complex numbers work the exact same way. Okay. Now the next thing that everyone has to understand, or you have to understand, is that this complex number right here, I'll just rewrite that in red. So Z0 minus A plus BI on Z0 minus C plus DI. Right, this complex number, right, it's a complex number. So the top and the bottom are both complex numbers. So obviously this form is called Cartesian form, right? And you can have multiple forms of a complex number, right? And another form of this complex number is polar form. So what I'm going to do is I'm going to change this complex number into polar form. So I don't really know what it looks like in polar form. So I'm just going to assume it has some magnitude R1, right? And it's got some angle alpha, right? And the same thing I'm going to do for the complex number on the bottom. So it's going to have some magnitude R2 and some angle beta. Now, if we go back to our diagram, we can actually have a look at what angle alpha and angle beta is, right? So angle alpha is the angle that the complex number AD makes with the real axis, right? So keep in mind, this is like this, okay? So if I drew a real axis right here, pretend real axis, right? This is the angle alpha, right? And if I do a pretend real axis here, right, it's more visualized here actually. So we can get rid of this, okay? And we can look at it here, okay? So here you can see that this is the angle alpha, and this is the angle beta, right? It's the angle that it makes with the real axis. So over here, you can clearly see that we're going to simplify this complex number. So Z0 minus A plus BI, right, on Z0 minus C plus DI equals, right? Now look at this, right? R1 is the magnitude or the size of the complex number AD, right? AD is the complex number that goes from the center of the circle out to the edge or the point on one of the points on the circle. So the magnitude of AD is the radius of the circle. And the same thing is for BD, right? BD is a point on the circle and D is the center, so it's just the radius of the circle. So R1 and R2 are actually the same, so they cancel. So we're left with cis of alpha on cis of beta. Now, at this point, for the people who know, right, there are a couple of cis properties that we're gonna need to use, right? So the first property everyone knows is that cis of theta, right, cis of theta times by cis of phi is equal to cis of theta plus phi. And number two is that cis of theta divided by cis of phi is equal to cis of theta minus phi, right? So in this case, we're going to use property number 2, and we're just going to simplify the right-hand side of this equation. So we keep the left-hand side the same, right, in this case, and we're going to simplify the right-hand side of this equation. Okay? And in this case, this becomes cis of alpha minus beta. Okay. So we found alpha minus beta, but what is alpha minus beta, right? So now the next step of this problem is to find some actual meaning behind alpha minus beta. So let's have a look at alpha minus beta. So alpha is this angle, right? And this is beta, right? So if you take this entire angle, right, and you subtract it from this entire angle, what you're going to be left with is the negative of this angle. Okay? And the negative of this angle is the negative of 2 pi minus 2 theta. It's the negative of 2 pi minus 2 theta. Okay, which simplifies to 2 theta minus 2 pi. Okay, so that's this angle, alpha minus beta. So what I'm going to do is I'm going to plug that all in, right, for alpha minus beta. So at this point, we can establish that z0 minus a plus bi on z0 minus c plus di is equal to cis of 2 theta plus 2 pi. Right, cis of 2 theta plus 2 pi, because alpha minus beta is cis of 2 theta plus 2 pi. So now what I'm going to do is I'm going to multiply the z0 minus c plus di to the other side, right? So I have z0 minus a plus bi is equal to cis of 2 theta plus 2 pi. And notice cis of 2 theta plus 2 pi, this will just cancel out to being cis of 2 theta, right? Because 2 pi is just a revolution. It's just a 360 degrees around, right? It will still end up at the same angle. And over here, I'm going to put z of c plus di. Now, at this point, what I'm going to do is I'm going to expand everything. So here is z0 minus a plus bi is equal to cis of 2 theta minus times z0 minus cis of 2 theta times by c plus di. Okay. Now, obviously, I'm going to group all the terms with z0 together because obviously z0 is the complex number that is the center of our circle. So I'm going to group that together because we're solving for z0. So z0, 1 minus cis of 2 theta, so that simplifies, is equal to a plus bi minus cis of 2 theta multiplied by c minus cis of 2 theta multiplied by di, right? Now at this point, what I'm going to do is I'm going to divide both sides by 1 minus cis of 2 theta. So z0 is equal to a plus bi minus c times by cis, cis 2 theta. I don't want everyone to get confused. So cis 2 theta times by c minus cis of 2 theta times by di. And that's all over 1 minus cis 2 theta. Okay, 1 minus cis of 2 theta. So this actually is the center of the circle, right? So obviously, if you know a, b, c, and d, you can just chuck it into this equation, right? And simplify the cises. So just find cis 2 theta, a, b, c, d all and just write them all down. And then once you have them in complex number form, put this in your calculator. And if your calculator is either an fx-991es or fx-991ex classwiz, okay, you should just change it to complex mode. Okay, and if you change it to complex mode, it will automatically simplify this expression for you. It will automatically simplify this expression for any a, b, c, d, e, f, g that you get, right? So this expression will eventually simplify. So it will simplify to z naught is equal to some x, so some real component plus some imaginary component, right? And so therefore, the center of my circle is x comma y. And now the next part of this is to find the radius, right? So defining the radius is so much easier, okay? So the radius, right? The radius is the same as if I took the distance between the center and one of the points on the circle. So the radius can equal the magnitude of the point A, which is a point on the edge of the circle, right? It's the same as on the edge of the major arc, minus the center of the circle, which could also equal point B minus the center of the circle, right? And it doesn't matter which one. For the sake of argument, I'm just going to use A, right? Now, A has the coordinates A plus BI, right? And Z has the coordinates X plus YI, right? So if you have it like this, what you do is you just simplify it. So it just becomes A minus X, right? Plus BI minus YI, right? And once you have the real and imaginary components together, you just find the magnitude and you'll get some magnitude. And that ends up being the radius, so the magnitude. And we're just going to call this magnitude R, okay? So therefore, all you have to do is to find the equation of the circle. It's just x minus capital X squared plus y minus capital Y squared is equal to R squared, right? And that ends up being the equation of our circle.